All right, the practice questions were on page 614, number 5. What is the period of a pendulum with a length of 0.45 meters? So t is equal to 2 pi root L over G. So t is equal to 2 pi root, the L was 0.45 meters, and for us, G is 9.81 meters per second squared. Type this in your calculator. You should get a t of 1.346 seconds. Number 5 is done. Number 6. What must the length of a pendulum be to have a period of 4 seconds? So again, t is equal to 2 pi root L over G, but this time you're looking for L. Divide both sides by 2 pi, and then square both sides. So you'll have t squared over 4 pi squared equals L over G, and you're solving for L, so multiply both sides by G. So L equals G times t squared over 4 pi squared. So L equals 9.81 meters per second squared. Told us in the question that t was 4 seconds. Remember to square it. Divide it by 4 pi squared, and try to remember to square your pi as well. And so when you do this, you should get 3.976 meters. Number 6, done. Number 7. Number 7 says, if every swing of a pendulum in a clock causes the second hand to move an angle representing exactly a half of a second, what must the length of the pendulum be to make the clock keep accurate time? So every swing is a half a second. So it starts up here, it swings over, that's a half second, and it swings back, that's a half second. So it's a fancy way of telling you the period must be 1 second, and it wants the L. So t equals 2 pi root L over G, divide both sides by 2 pi, square both sides, t squared over 4 pi squared equals L over G, so L equals GT squared over 4 pi squared. 9.81 meters per second squared times 1 second over 4 pi squared. And when you do this, you should get an L of 0.248 meters. Number 8 says, if a pendulum has a period of 0.36 seconds on Earth, so t Earth is 0.36 seconds, what would be its period on Mars? So I had said to you earlier that the G was on page 133 or 134. For Mars, it's actually 133, and it's 1.64 meters per second squared. So that's for Mars. So the first step is to get the length of the pendulum, okay, on Earth. So we just rearranged it like twice here, so I'm going to cheat. L is equal, so from t equals 2 pi root L over G. You're going to rearrange and get L is equal to GT squared over 4 pi squared. So on Earth, the G is 9.81 meters per second squared. Told us the period on Earth was 0.36 of a second. Square it over 4 pi squared. And when you do that, you get an L of 0.322 meters. And now you take that L and you go to the moon. So t is equal to 2 pi root L over G. So 2 pi root 0.322 meters. And on the moon, the G is 1.64 meters per second squared. And so you end up with a t of 0.88047 seconds. Now, if some of you Googled the moon, you might have gotten a slightly different G, and so your T would be a little bit different, but don't stress, that's okay. Okay, so those are the 4 from the textbook. I also ask you to do the last 2 on the sheet of conservation of energy and momentum questions with simple harmonic oscillators. So number 7 from that sheet has a block, and it says it's a 3 kilogram block sitting on a horizontal surface, frictionless, attached to a spring, makes one complete oscillation every 2 seconds, so t is 2 seconds. The maximum velocity, so here where x equals 0, the maximum velocity is 5 meters per second. What is the amplitude of the oscillation? So how far out do you pull it out here? X equals what? When out here, v equals 0. Okay, so because we have t, we can do t equals 2 pi root m over k, and we can find our k. Divide both sides by 2 pi. Square both sides, so t squared over 4 pi squared equals m over k. So k is going to equal 4 pi squared m over t squared. So 4 pi squared, 3 kilograms over 2 seconds squared. And when you do this, you get a k of 29.6088 newtons per meter. So that's our k, but the question wants to know what's the amplitude. So then we go to our energy equation, 1/2 mv initial squared, mgh initial, 1/2 kx initial squared equals 1/2 mv final squared, mgh final, 1/2 k x final squared plus E lost. No E lost, no mgh. If I call this my initial out here, then there's no speed, but there is a 1/2 k x initial squared. And in my final, there's no x, but there is a 1/2 mv final squared. The halves cancel, and I am looking for amplitude. I'm looking for x. So x initial squared equals mv final squared over k. 3 kilograms, 5 meters per second squared over the 29.6088 that I just found. Newtons per meter. And remember, that's x squared. So before you take the square root, you get 2.533 meters squared. Take the square root, and you get 1.59155 meters. Okay? Number 7. Number 8. I have a block sitting on a frictionless surface. Tells me the k is 20 newtons per meter. Maximum velocity, so here at this point where x is 0, v max is 3.5 meters per second. All the way out here, x is 2.8 meters, v is 0, and it wants to know what's m. So 1/2 mv initial squared, mgh final, 1/2 kx final squared equals 1/2 mv final. Oops, that's initial, sorry, initial. Mgh final, 1/2 kx final squared, E lost. So no E lost, no mgh still. If I call this my initial spot, then it doesn't have a speed, but it does have an x, and in the final spot, it doesn't have an x, but it does have a speed. So 1/2 kx initial squared equals 1/2 mv final squared. Halves cancel, solving for m. So divide both sides by vf squared. Initial vf squared. Not going to get to the part B. K was 20 newtons per meter. X was 2.8 meters. Remember to square it. Divided by 3.5 meters per second, squared as well. And when you do this, you get 12.8 kilograms. Part A. Part B wants to know At what location will it have a speed of 2 meters per second?